Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So today I'm delighted to be joined by Professor Paola Cinnella. She's a professor of fluid mechanics at Sorbonne University in Paris, and she's also the new director of the Sorbonne Cluster for Artificial Intelligence, also in Paris. And what I found particularly interesting about her career is that she's not come through AI through the usual, computer science route. She is very much mechanical engineering and fluid dynamics specialist. We talk about where she started in Italy, the transition to France, moving back, the idea of, academia having to move between different countries to secure the tenure positions, how challenging it can be, especially for family and personal life. But she really, I liked her passion for fluids. She talked about working on these exotic dense gases and real gas effects, and how some of those led her towards the uncertainty quantification and Bayesian methods, and working with statisticians helped her then realize that she could do the same around machine learning, and really wanting to collaborate with different disciplines and different groups. And in some ways, she's represents a very important bridge between what we might call, classical CFD, numerical methods, turbulence modeling, and this new world of AI for science. And she's played actually a major role in the wider CFD community. She's an editor-in-chief of Computers and Fluids, associate editor for International Journal of Heat and Fluid Flow, and she also helps to coordinate the ACOFDAC special interest group on machine learning in fluid dynamics, which has led to a really successful conference series, this ML-for-CFD, that I have been fortunate to have helped her a little bit as well. But really, she is an educator, she is an academic, and we had a really interesting discussion as well on what it means in this new era of AI. What's the valuable thing that we should be teaching new students at undergraduate and postgraduate level, and really what is the potential for methods. And one of the things we talk about is the differences between surrogate modeling and turbulence modeling, and how could they be interconnected? When is the value of those? And we finish off talking a little bit on the AI for science and how there is this opportunity for cross collaboration across disciplines. So she is somebody that I am inspired by and always enjoy working with. And I hope you enjoy learning more about her and her work in this conversation. So sit back and enjoy this conversation with Paola. So yeah, thanks for coming on this. Really appreciate it. I've loved working with you on various projects over the years, but this is a good opportunity to hear more about you and what you do. And I guess maybe as a starting question, you started in mechanical engineering in classical fluid mechanics, I guess, and then you've moved through now into machine learning and AI. Mm-hmm. But how did all that happen? Rewind. Where did this love for fluid mechanics start?
Well, when I started, so I had to choose a university. I wanted to do fundamental physics. I wanted to go to fundamental physics, astrophysics or something, or to mathematics. And my mother said, no, this is not a good job because the only opportunity for you is to become a researcher. That's not well paid. So be an engineer. So go to engineering. And then I started to do civil engineering, actually. And after 1 year, I discovered that I didn't like. And I started to look for things which were closer to physics and to mathematics. And a friend of mine said, I'm doing fluid mechanics. There's quite a lot of mathematics in that and also some physics. So try it. And that's how I went to fluid mechanics, and I did like it. Actually, my professor in Italy is Michele Napolitano. He worked with NASA. He had a PhD with Stanley Rubin, who was actually one of the first editors in chief of Computers and Fluids. And he gave us a book by Shapiro. It's Fast Profiles. I think it's a book. Shapiro is a professor. He was professor at MIT, I think. And he said he gave us that book the first day of the classroom, and he said, if you don't like this book, you can take another course to just abandon the fluid mechanics option. And I read it and I loved it. So, and that's how I made fluid mechanics. So that's the origin. Yeah.
Interesting. And then, did you always want to go and do a PhD, or were you sort of debating of going into industry or something?
Yes, because, my family, my family is a family of professors. Well, they are professors more in the secondary school, but they all did high studies, let's say university and so on. So I wanted to be a professor, and I wanted to be a researcher. First of all, in the first place, I wanted to be a researcher. And so I knew that it was necessary to have a PhD for being a researcher. And so, since the beginning, I was looking for a PhD. And at that time, it was very hard to have a PhD in Italy because there was no tradition of PhD, I would say 30 years ago. Mm-hmm. And people went abroad for the PhD, actually, because in Italy, it was not very valued. It was at the very beginning. I was maybe the 11th cycle of PhD, which means that the PhD degree in Italy was created 11 years before I start. So it was relatively recent. Mm. And there were very few fellowships for a PhD, so it was very difficult to have them. And that's how, at some point, I decided to move to France. So, and then, I loved France and remained here.
Yeah. Okay. And your topic was on more numerical schemes, more like compressible terms. How did you get to that decision, I guess, on the topic?
Actually, at the very beginning, I was doing schemes for incompressible flow. It was, I started with the lid-driven cavity and the velocity-vorticity formulation of the Navier-Stokes equation. So that was my master thesis. But then, when I was looking for a PhD in France, actually, the beginning should have been just a second master degree. And after, I decided to remain for the PhD in France. But anyway, so my supervisor in Italy knew Professor Alain Lerat, who was one of the founders of the IC-CFD conference too. And he said, I know this guy in France is doing a good job but it's compressible. So it's another thing. And if you are not scared about compressible flows, you can go to him. And he's very good. He's doing numerical schemes and so on. And so that's how I decided, Paris is not bad. Actually, it was because of Paris more than because of the compressible schemes. Because my options were to go to the von Karman Institute, to go to the US, or to go to Paris. And, I said, Paris, I have to go to Paris. And so I arrived here, and Alain Lerat proposed to me to work on high order schemes, which were a quite recent topic at that time. At that time, high order was second order schemes, actually, because everybody was doing first order. So second order scheme were already high order. And he said to me, we are going to move to third order. Okay, yeah. And that's to do unsteady flows, because at that time, people were mostly doing steady Euler or steady Navier-Stokes. And so, I started a PhD for a high order scheme to capture unsteady phenomena, even if it was only runs at that time. And yes, it was a high order finite volume schemes. And then I spent quite a lot of my career on high order scheme because of that.
And was it therefore a natural progression to continue going down the route to sort of postdoc and faculty position? Was it just an evolution, or was it a challenge to progress down that route?
It was a challenge because, as you know, there are not many positions in academia. They are very challenging. Also, I was in France. I spent quite 1 year, because the second master degree, and then 3 years of PhD in France. Mm-hmm. And at some point, I wanted to go back to Italy. And in Italy, there were 0 positions, basically. So I passed the competitions in France, because in France, the positions are open. You have to get a qualification, which is a national qualification. So this depends on how many papers, if you have taught courses, not, and so on. And it's basically a sort of minimum certification, which says, okay, you are fit to be a professor. Okay. Not a professor, but an assistant professor. Mm-hmm. And then once you have once you got the qualification, you have to apply at the universities, which have positions open, and you have to compete with other guys. So I eventually got a position here in Paris, but I wanted to go back to Italy. So I renounced to the position, even it was ranked first. And I decided to go back to Italy. And there I started with a postdoc, because there were no permanent positions open. And after some time, after my postdoc, I moved to a close by university, because, my home university is Bari. It's in the south of Italy. It's Apulia. Mm-hmm. And I went to Lecce, which is even more south. It's the very tip of the hill. And there I got eventually a faculty position, and I worked there for 8 years as an assistant professor. And I was the only assistant professor in fluid dynamics of the whole university. I was the only one. So,
wow. Yeah. And what was your main focus back then? When did this move to the RANS modeling and certainty quantification and things like that? Was that during that period, or was
yes. Actually, when I arrived in Lecce, I was, as I said, I was the only free mechanicist, and I was in part of a larger group in energetics. And I started to think about what could I do, which is related to energetics. And I discovered, almost by chance, dense gases. And so dense gases are compressible. So it's gases, so it's compressible flows of organic fluids, which are governed by complex equations of states. Could be supercritical CO2, but it's a light gas. But you can have denser gases or more heavier gases, like refrigerants or hydrocarbons. And these gases are used in industrial processes, or also in some thermodynamic cycles, like, of course, the refrigeration cycles, but also direct cycles, which means, for instance, organic Rankine cycles, which are like the Rankine cycle, which works with these strange gases instead of water. And the problem with these gases is that since it is industrial fluids, they are very ill characterized. Actually, you don't know exactly about the properties, about the equation of state you should use. There are few data. The material properties are given in only technical sheets with a lot of uncertainties. And that's how I came to uncertainty quantification, because at some point I discovered polynomial chaos stuff and so on. And I said, oh, this is perfect, because I have a fluid where actually I don't know exactly how it behaves. So I would like to characterize the impact on the CFD solution of the bad knowledge of the fluid properties. Not only the thermodynamics, but also the transport properties are not very well known. And so, that's how I moved to uncertainty quantification. But at the beginning, it was not RANS. It was even Euler, but you don't know exactly the thermodynamic. You cannot characterize completely the thermodynamic behavior of your gas, because you don't know which equation of state you should use, and the parameters of the equation of state are, not very accurate.
That's interesting. So it was more driven from that. Yeah, I guess Did that help you working in a more complex area in a way? Did it give you more understanding of the fundamentals of fluid mechanics? I guess when people just study single phase, simple, incompressible, maybe they don't appreciate the complexity.
Yeah, actually, I adore those gases because, well, at least theoretically, they could exhibit very exotic behaviors. In particular, they are expected to exhibit under some thermodynamic conditions. If you take a heavy enough gas, it is expected to exhibit expansion shockwaves. And actually, there is a community around that, which is called the non-ideal compressible fluid dynamics community, which has spent several years trying to have an experimental proof of the existence of these expansion shock waves in single phase compressible flows. So the first one to postulate that is Hans Bethe, so the physicist Hans Bethe, Nobel Prize, who showed that for van der Waals gases with some values of the polytropic exponent, you can get a region where the second principle of thermodynamics forbids the classical shock waves, so the compression shock waves. So instead you have a compression fan, and conversely you can have expansion shock waves and instead of expansion fans. So everything is reversed. And then several researchers work on that. Thompson, Michael Kramer at Virginia Tech, and so on. And people were fascinated by these gases because everybody wanted to prove experimentally that was possible. And eventually there was a group in Russia at some point who did an experiment with FC70, which is a fluorocarbon, those which are very, very bad for the ozone layer. So they did an experiment with this, and they said, "Oh, here you have the expansion shockwaves." But then the people started to challenge the experiment and said, "No, this is impossible. Probably it was two-phase," and so on. And then in Delft there was a group, so the group of Piero Colonna. There is a big group in TU Delft who tried to reproduce an experiment with different gases. Also, you have Alberto Guardone in Milan. He got an ERC actually on that. And but it's very, very difficult because these expansion shock waves exist in a very tiny thermodynamic region, and all the uncertainties associated with the shock tube, with the membrane breaking and so on, can perturb the actual development of the shock wave. And so we are never sure it's really a pure expansion shock wave. So, well, the interest of that, besides the scientific curiosity, was that some people were expecting that you could exploit this behavior to get a better energy conversion cycle with the reduced losses and so on. It has been abandoned right now a little bit because actually, there is a very small industry supporting that because it's very specific machines. And it's very small companies working on that with few funds to invest in research. But it was a great period. So it was actually, and also it has impact, even if you don't find the expansion shock waves, at some point you don't care because there are plenty of systems with real gas effects, not expansion shock waves, but still real gas effects, and that you need to characterize to have better conversion cycles or better heat pumps or, all this stuff. And so we are still working on that. So we have right now a project ongoing with the German team. We are doing the simulations and the machine learning, and they are doing the experiments, and it's a very nice team. And
very cool. And you mentioned at the beginning that you were in Italy, you went to Paris, you went back to Italy. What then was what led to you, going back to Paris again?
Well, again, it's not easy to stay in academia in Italy because the funding system, the academic system in Italy is chronically underfunded, but severely underfunded. That's why you find Italians everywhere, actually. I've noticed maybe that there are lots of Italians everywhere. So the academic position are very few. I had one actually, but then you are alone. It's very difficult to get funding. The possibility of having a career are so you have to be very patient, you know. And also my husband wasn't Italian, and he never could find a satisfactory job in Italy. So at some point he said, well, let's go back to Paris. And there I applied because I wanted to move to a professorship. I was assistant professor. I wanted to move a professorship. And I got a position in Paris. And that's how we moved back to Paris, because he also had a job here in Paris.
Okay. I understand. So you, well, as you say, Paris is not such a bad place to be.
It's easy for two persons. It's easier to find both a job in Paris than find both a job in southern Italy.
Yeah, but that does tend to be, I guess, an overriding thing of academia, that it's almost this necessity to move, right? It's kind of a weird profession, even in the US or the UK. Very few people will have their entire career at one place, particularly earlier on. They will have to. Have you found that it's almost it's a fairly unfair thing in a way, that you have to move your family and do things just to progress?
Yeah, that's true, and that's because, well, for instance, in France, there is even a rule in some disciplines, like in mathematics, that if you have been an assistant professor in a department, you cannot be a professor in the same department. You have to move to another one. And in small cities where you have just one university, it's basically, this means that you have to move. So this pushes a lot of people to abandon the idea of moving to a professorship, and they remain assistant professors for forever. Also because the French system allows it. It's not like the tenure track in the US. If you are not promoted to associate, then you have to leave academia. You can remain as associate professor with a permanent position forever. So if you can't move with your family, basically you cannot progress in your career. And so it's a choice. Some people are happy with an assistant professorship for their life. They do teaching and so on. But if you want to move, so if you want to progress with the career, yes, I don't know, the academic world is built like that. Why? Don't know exactly. It's also part of science to move. If you look in the past at the former scientists, where they were moving quite a lot, you know, even in the Renaissance, you know, you had this, I don't know, Galileo or Leonardo da Vinci. They were moving around, and that's because you need to spread knowledge, to find better environments. So I think it's nice. The difficulty is when you also have a family life and you have two persons to move. In some cases, it's easy because one has a flexible job or stays at home, but otherwise it can be, quite challenging. And I think it's something that the new generation don't appreciate that much, because, you know, I think I am, what's my generation? I think Generation X. And we are, you know, I know that my children say, your Generation X is the generation of suffering. You know, you were raised to suffer, but it's no longer the case.
But it is a serious point, though, that I almost feel like sometimes academia has, maybe not to be careful, but I'm just amazed at the dedication it requires to get through it and to become someone like you, you know, a top professor. Like it feels I feel like probably many people aren't able to get to that point. One, obviously they're not intellectual enough. They're not, you know, capable enough, but also you have to have quite a determination to get there, which is probably partly a good thing, because it's like survival of the fittest, I guess. But as you said, to some people where they just really would love to stay where they're living because they have friends and family and they can't. It's a shame.
Well, what I used to say to my PhD students is that the academic career is kind of similar to a career in music or in theater or in a high level sport. Okay. If you are a musician, if you are a pianist, or if you are an opera singer, you have to move around. And it's a very competitive field. And you do that not because you want, a quiet life, but because you are passionate and you want to be on the stage and see, people around you clapping hands. And, it's a sort of, I think that, there is a sort of narcissistic side, maybe in people remaining in academia, but also, it's an intellectual work. And, I guess that, if you do that because of passion. First of all, it's not an ordinary job, actually.
Yes.
And you want to push the frontiers of knowledge. You want your work to have an impact, and you want to do something to move things forward, and that's a passion. So it's maybe you don't make it, but you still try because it's like a football player. Not all football players are Lionel Messi or I don't know, David Beckham, but they still fight.
That's a very good. I've not heard it described that way about a musician or sports players. It's kind of true that they also move around a lot, and I get that's the old thing though of universities, isn't it? That you almost have to wait for the person above you to, retire or die to get their position. So people end up also moving around because there's sort of not enough. Where I guess in a big corporate world, people are more able to, maybe that's changing, but in like an Airbus or something, I'm sure there's jobs for life almost just in one company where academia. So I say that because I think people should appreciate just how hard it is to get to being a professor, that it's not just an intellectual thing, it's like a determination and passion thing, as you say, to do it. And so, talking about, wanting to be at the forefront, I mean, you were quite early on looking at sort of Bayesian learning and data-driven turbulence models and machine learning. When did you start to get into that? When did you get a sense that these methods were an alternative or an enhancement on the more traditional numerical methods sort of line of research?
Well, actually, I stepped into Bayesian methods when I was doing uncertainty quantification for dense gases. And at some point, I was discussing with some colleagues of mine from the University of Trieste, and they had a sort of startup. I don't know if you know this startup called Esteco. They produce a software called Mode Frontier.
Yes, of course. Yeah.
Okay. And so, they were actually promoting this software in universities. And they sold also academic licenses and so on. And so I started to discuss with them about my problems with uncertainty quantification in dense gases. And they said, okay, but you could try to solve an inverse problem and so on. And so I started to look into the literature, and I started to be interested into these Bayesian methods. And I said, okay, this could work for dense gases, but the thermodynamics is not the only source of uncertainty, because you also have the uncertainties associated with the turbulence models. And these are very old problems. So there are so many turbulence models. You don't know which one you have to choose. You don't know which parameters you should put into them and so on. So let's try to quantify this statistically instead of just using expert knowledge, which is what anybody does actually, because every company actually has sort of established know-how, saying, okay, for this problem you should use the K omega SST. For this problem you should use the Svala-Talmaras. For this problem, you should use that one. And sometimes you also know that they retune the parameters. For instance, I know that people in internal combustion engine used to recalibrate K epsilon for having better results for internal combustion engines. And but all this was tuned by hand, basically. And I said, okay, if there are clean mathematical techniques to do that, let's try to use them. And so, since I was already doing direct uncertainty quantification, I started to try to do the backward uncertainty quantification. And at some point, well, it was a bit hard for me because, in mechanical engineering, we are not very well trained in probability and statistics. So eventually I studied that myself because I was interested into that. Actually, I also taught a little bit, but it was not enough to, understand all the details. And so at some point I was invited by a statistics department in Chile. And they invited me for 2 months. And I was there with statisticians and mathematicians of probabilities. And during the first month, it was impossible to understand each other because, I was calling things with names that they interpreted in another way and so on. But at some point we started to understand each other, and that was great because some papers which were, just hieroglyphs to me, started to be clear, and that's where all the Bayesian stuff was set, and I could start to recalibrate the turbulence models and so on. So the fact of being in an interdisciplinary environment and talk with mathematicians was extremely useful to me, not only with engineers, even if I love engineers, but sometimes like.
No, that's a very good point, and I guess even to today, that's a challenge on the machine learning side, isn't it? That maybe it's starting to change in a course today, but I guess most people who are doing the research, therefore, who studied, 5 to 10 years ago or more, didn't have any of that background in computer science or in statistics or sort of methods that maybe people who did more maths, stronger maths may do it, but engineering courses probably wouldn't. I mean, how have you seen that affect the machine learning side? I know you've been quite passionate about connecting. I know you kicked off, for example, with the extrality and AirfRANS datasets, and do you try and take some of that inspiration of your time getting familiar with statistics and try and do the same on the machine learning side?
Yeah, definitely. Actually, I had the chance when I moved to Sorbonne to be in a very interdisciplinary environment, and at some point I stepped into the team. We have a very strong machine learning team here in the computer science department. And I discovered, almost by chance, that they were doing machine learning for physics. So I contacted them and said, okay, I'm a fluid mechanicist. I'm trying to move to machine learning. I know that you're doing machine learning and you're trying to move to fluid mechanics. Can we do something together? And so we applied together to an internal funding instrument of the university, and we got funded. So we had this LearnFluidS team. So it was a little bit of money to have a postdoc and a few interns, little things, but this allowed to connect each other. And then they said, hey, we have this guy who is going to do machine learning methods for CFD. So we want to, but we have no databases. Machine learning, we have MNIST, we have, many famous databases, but there are not bad databases in CFD. We want to build one, but actually we don't know exactly how to do the meshes because they were trying to use, OpenFOAM, and they were using, Snappy XNet.
Snappy, Yeah.
Yeah. And of course, the meshes are not very good close to the wall. And that's the point. So I said, no, but you can also use structured meshes and so on. And then also we started to discuss a little bit about the criteria we had to use to evaluate the results, not only the MSc. We have discussed that, and that's how, well, eventually they produced this AirfRANS. Of course, the merit is essentially the students. It's also interesting that this student had a background in physics at the beginning. So, and he moved to machine learning too, but he had a background in not in CFD, but in physics. And so with this mixture of disciplines, we came up with this database, and also they could test a lot of baselines. The way they do it in machine learning, they take one baseline, two baselines, and they test all the baselines. And now we are trying to do more, actually, also for unsteady flows. So hopefully we will have a new database coming out, which is on LES. So this time it's not steady runs, it's more LES, and it's actually snapshots, because to have time resolved predictions.
Yes.
And the idea is the same. So they enlighten me on machine learning architectures, because they know better. They know better also sometimes the pitfalls and the difficulties you can have in training these things, because sometimes, the training is not an easy. But on the other side, I say, okay, maybe you should look at this and that. You should use these physical criteria and so on. And it's very, very instructive, I think, for both sides. So I'm very happy with this collaboration. And that's how we.
I mean, how much have you struggled, though, to get acceptance in that from when you started to now? How have you seen things progress? The argument of how well is the model just a fancy interpolation versus actually learning the physics? How much is a good thing that there's these hard questions, and how much of it is almost holding things back a little bit?
Well, they are the same. Well, I started with the turbulence models, right? And it was hard in the beginning because, turbulence models have a lot of knowledge. They are really incredible. They have this physics sense, which is, I don't know. But they are also very, fond of their methodology. They, the fact that you have to do the things in a certain way. And also the parameters the model parameters been tuned, making a lot of compromises and so on. So they don't like that you start playing with the parameters, playing with the terms and so on and so on. And for sure, at the beginning, the community of people who was playing with machine learning or calibration, also calibrations of turbulence model, was not a community of turbulence modelers. Was a community of people coming like me from numerical schemes, actually, or from numerics in general. And so we didn't have the right codes for turbulence modeling, which is, there is a lot of knowledge accumulated for decades. And so many people were doing things that were not acceptable, actually, from a strict turbulence modeling point of view. So they were not using the right features as the input of the turbulence model. For instance, some people were using velocities at the beginning, which, it's non-Galilean invariance and so on. And however, still, this model looked interesting, so everybody was intrigued with the possibility of having a turbulence model. Because in the end, if you look at even to the traditional turbulence models, they remain data driven. They are data driven with a human, tuning the parameters, but they are data driven actually, because you are calibrating on some data sets, which are the canonical flows. But okay. So at some point, you had Chris Ramsey, which who decided to organize a meeting it was in Virginia. It was at what's the name? The Lighthouse.
Lighthouse.
Right, the Lighthouse. So there was this mythical meeting in 2022 where he said, okay, we are going to put around the table classical turbulence modeler and these guys, these parvenus with their machine learning stuff. and it was really instructive because you had incredible guys there. So it was in honor of the 60th birthday of Philippe Spallard, who is a great guy, by the way. And you had, Philippe, you had Paul Durbin, you had all these guys, who know plenty of things on turbulence modeling, and they were explaining things. And on the other hand, we were trying to defend the idea of using machine learning. So we were a little bit, how do you say?
Under attack.
Under attack. But it was instructive because I think thanks to that, we progressed a lot because we started with the idea, okay, it's nice. We just fine tune a model for a very narrow set of flows. We get better results. We are happy with that. And now we are moving more and more toward unified models. And maybe, I may be too ambitious, but never know. Maybe in 10 years more, we could have a foundation model, data-driven turbulence model, which could, actually realize the dream of turbulence model of a universal turbulence model. I'm not sure we will get there, but,
it is interesting though, because in some ways, turbulence modeling was going out of fashion. And I know that it used to be the joke, didn't it? I think that for a European project, if you said you're going to work on turbulence modeling, it was almost like guaranteed to be rejected because it was seen as a solved problem or, what's new. Yeah. And, but the irony is that industry still uses mainly RANs and are stuck using methods from the 80s or early 90s. It seems like with machine learning, then there was this spike of potential again. But I don't know about you, but I almost felt that maybe some of the use of machine learning for turbulence modeling was a little bit early, and the expectation was so big that when it didn't meet that expectation, it sort of then dropped down again. But I agree with you that in some ways, with the idea that we want to build also foundation models from a surrogate modeling side, having to do everything with LES or whatever, it's just so computationally expensive. Ironically, if you could use machine learning to come up with the ultimate turbulence model, you would actually make it much more affordable to actually run the simulations to achieve. So I feel like now there is maybe a little bit more economic or relevance again of the turbulence modeling because it would save so much on the data generation side. But it does seem to be, I don't know if you've noticed, but I saw in CFD anyway, that initially everybody was focused on machine learning for turbulence models, where now it seems to be far more about machine learning for surrogate models. And that seems to be much more focused on, and you don't hear as much on maybe the turbulence modeling in such a strong way. Would you tend to agree with that the community sort of shifted a little bit?
Some communities, yes. I think in complex engineering applications like car industry or even in solid mechanics, for instance, they are shifting in that direction. I think that in aerospace, they are still interested in turbulence models, especially for complex applications like hypersonics or transition models, all that. That's because, even if you can, what you would like to have for instance, in aerospace, what you would like to have is a high fidelity model, so like LES quality, and to perform your optimization with that. Why? Because we know that RANs has flows, because we want to explore extreme operating conditions. because we are moving away from known paths, like we are changing the fuels, we are changing the architectures, and so on. So you cannot just design, a new propeller or a new wing based on epsilon modifications of something and for which that the turbulence model is going to be wrong, but more or less how it's going to fail and how you should correct it. Okay. And the problem is that even if right now with the portage to GPUs and so on, high fidelity simulation are becoming more affordable, still that's one simulation. If you want to perform an optimization, you need thousands of LES. And even if you can run a complex world model LES on a GPU, chatting, this, but still it's one. So if you want to perform, 2,000 simulations, you need 2,000 GPUs, which is very costly. I don't know how many companies can, afford 2,000 GPUs, but they're on. And also, if you have, few GPUs, you have to wait for many, many days. And the design cycles need to be shorter for economical reasons and also for environmental reasons. So for that, you cannot rely on LES alone. So what you can try to do is to distill the knowledge of this high fidelity method into lower order models. Yes. So how can you do it? So that's the way I try to do it. One possibility is to distill this into augmented RANS models. And then once you have augmented your RANS model, you use that one to perform the optimization cycle, which is much more affordable. Provided that your model generalizes well enough, at least on your design space. Because if the model fades as you move a little bit far from the baseline, that's useless. The other point you can do is to use surrogate models. Okay. But the problem with surrogate models is that you will never have enough LES to train a surrogate model only on LES. So you are trying to do that, right? You are trying to produce high fidelity databases, but they are still relatively limited. And I don't know how many of them will be possible to produce, especially for very complex, very high Reynolds number flows. And if we have so many data at some point, what's the point of having surrogates? If we can run thousands and tens of thousands of LES, what's the point of having a surrogate? So I don't know. So maybe what we are trying to do is to have multi-fidelity models. So where actually you train the model using data of different origins, provided that you have a clear hierarchy. And you can actually try to train using plenty of low fidelity data like RANS. So that's where having a RANS, which is not too bad, remains useful. And then you try to learn the gap between the RANS and the high fidelity, and then you use your surrogate. And this is something which is not yet so used in the surrogate modeling community, because they either use plenty of RANS data, or, you have some databases, high fidelity databases, like the one you have contributed to produce, but still in a database you have 300 cases for a family of cases, but it's not enough to have something which can be reused for anything. So this means that every time you change, you need to run 300 LES or one model LES or whatever, and that's costly. Yeah. And so.
No, so that's kind of why I think there is a connection between the two for sure. That the underlying CFD is still the key, and making that more affordable. Yeah, you're right. There are startups like Volcano and others who are trying to come up with very computationally efficient codes, but that is kind of the whole point of turbulence modeling in some ways, is to try to come up with a way of modeling it in a clever way. So yeah, if it can be done, then that would be good. I did want to ask you on you're an editor-in-chief of Computers and Fluids. You're extremely active in the academic world when it comes to publishing. How are things changing with the rise of like ML-based papers? what standards should they be having? You know, you previously would always say, I want to see a mesh refinement study. I want to see proof of convergence. I want to see, you know, what standards are you wanting and seeing? And yeah, I'd be interested to hear your thoughts as a journal editor.
Yeah, what we are doing right now in Computers and Fluids is to ask, to motivate very well why you do need machine learning and why this is improving over, I would say, standard approaches. To give you an example, many people do, we were talking about surrogates, and they say, I want to design a new airfoil, new airfoil. And for that, I generated a database of 10,000 run simulations, and then I trained the surrogate, and then here goes my optimal profile, optimized using the surrogate. But if you have the computational power to run 10,000 runs, you can do brute force optimization. You don't need actually the surrogates, right? So what we are trying to ask is to show clearly that you are learning something more than, so your method is bringing something more, either in terms of total computational time, including the time required to generate the database, and in terms of improved design, or showing that you are making up for some failure of the classical model, because otherwise showing, I train a surrogate, it works well, here's the optimum. It's not, I believe it's better, but you are not telling the community what's new with respect to things which already are able to do. For instance, in some cases, we have tested some baselines on airfoils. You can generate an airfoil solution, a full field runs in 5 minutes, using FreeFEM or any code. Okay. To train some surrogates, you need 20 or 25 or 30 hours of GPU time. So in 20 hours, I have largely finished my optimization with my old runs code. So the point is to show that either you go to more complex models and you can do that fastly. So you have, each run simulation would take, 100 hours. And thanks to the surrogates, I'm speeding up and I can have it in, 20 hours or 24 hours. Or it's not new. So what we are asking is that, not only show that your model has been trained well and it performs better, but also try to compare to classical methods, show what's wrong with the classical method, what your new machine learning method is bringing, and also show eventually where your machine learning method is going to fail, because that's also important, not only showing positive results, but also negative results. And that's something the community doesn't like to do too much, because it's easier to publish when you have good results.
That's a very good point, actually. I think if you look at like NeurIPS or those papers, conferences, they mandate like a limitations section where you have to put down all the bits where you didn't do it. And unless I'm mistaken, that precedent of very clearly pointing out where the limitation is not something that's traditionally done, right? Not in such a clear before the conclusions, limitations. And I've often felt that there needs to be more transparency also from just the CFD side where things are bad. Show me examples of machine learning, for example, where if I pick a certain split or I pick a thing, I get really bad results. It's actually quite important, or else the conclusion is that these models are amazing and standard CFD's gone, rather than pointing out their positives and where they failed. The classic one, I guess, is in distribution and out of distribution, where
Exactly. And the other point is to evaluate the models. This is also discussion we have had elsewhere. Compare the model on CFD criteria. not only on machine learning criteria. Because, mean squared errors are the standard in machine learning. They are useful, whatever, but they can be also, misleading because, in particular in external aerodynamics, where most of the flow is uniform, basically you are training a neural network to capture a constant function. And the regions where something is going on, which are close to the wall, are very tiny. So if you are wrong in that region comparatively to the whole, to all the points you have, maybe it's not enough to have a clear signal on the MSC, but you see it if you plot velocity profiles, if you plot pressure distribution. In general, they are very bumpy. If you plot skin friction is terrible because in that case, you are not only reconstructing the flow field, the velocity field, you are taking the derivatives. And it's well known that approximating the derivative of a function is more difficult than approximating the function itself, right? And so in the machine learning community is not used to these criteria, which are the standard criteria in CFD. So again, I think that if you pretend to, if you say that you are going to replace standard CFD approaches with machine learning, then you have to show that machine learning is able to provide the same thing that the CFD code is able to provide. Yeah.
And funny enough, I was having this discussion on a paper we're putting out where it's also the case, isn't it, that in machine learning, because you have, let's say, 300 or 100 or 50 test cases, you'll average over them and as your number, where that has the same risk of some are really bad, some are really good, and then you have lots in the middle. Or is it you have lots, how bad is bad, how good is good? And this isn't fully explained just by a single number. So this, as you say, almost doing a deeper analysis and showing, I guess that what someone described to me is they, to the earlier point of like hype, because of the way the results are presented today, where an R squared value or even an L squared gives such low errors, it looks like they're perfect. But then when they try it in practice and they don't see as good, it almost creates a disappointment, which if the paper had shown it, they probably would not be disappointed because it would just be meeting the expectation where, so I would agree with you. Part of that is down to the way that the results have been presented in a way.
There is quite a lot of overselling, but that's because of the economical model also, because and the publication system, which is a bit too, especially in some countries. It's not the case in France, but in some countries there is huge pressure for publication, for being the first, for there's this talk, and I think this rush to publishing more and more in higher impact journals and so on, in the end is increasing the signal to noise ratio at such a point that people not even read the papers, they just read reviews of paper which are automatically generated by AIs. So there is something fundamentally wrong in this, because we should remain at a reasonable level where humans are talking to humans, because we are trying to produce human knowledge in the end. Because what's the point if all the AIs talk to each other? What are we going to do as humans? I'm going to look
just
at
go to the beach.
Well, go to the beach is maybe not bad, but you cannot stay on the beach all the year. Winter, you have to find something else to do. I think that we should maybe slow down a little bit and do what people used to do some years ago, which means publish less, but publish more thoughtful papers and wait a little bit before publishing. And when you publish something which is more complete. You have looked to all the consequences and, thought to all the possible,
Yes. I do know what you mean. This is the good and the bad thing of things like archive, where there's almost a sense of let's get it out there, We want people to see it. It's a preprint. The preprint's supposed to be taken as, well, this hasn't been reviewed yet. But unfortunately, people just take it as the main thing. And because things are moving so fast, the fact that it hasn't been reviewed is sometimes almost ignored, by people in a way. So I agree with you there. The pace necessitates sometimes to put it out, but at the same time, that feeling in your back of the head of going, well, I could really do with another month or two to really deeply investigate this, is balanced against the desire just to get something out. It's a tricky one.
And on the other hand, the standard editorial system is being flooded by papers. So it's becoming more and more difficult to keep quality in the review process. When you are flooded by tens of papers every day, okay, and you have to process them and you have to send them to reviewers. You have to find reviewers who are also flooded by other journals, because there are many journals, okay, many journals, and more journals are being created and so on. So at some point, it's just, it's just an escalation, and it's very difficult to control the quality of the papers. And in fluid mechanics, things are becoming difficult, but they are still under control to some extent because it's a small community. But you have seen the examples of these big conferences like NeurIPS, where they have tens of thousands of papers, where most of the papers are written by AI and reviewed by AIs. And so what's the meaning of the review process? In that case, you don't review it at all. You just put it for free on a website, and who wants to read it? So I think that the rush to having more and more papers, which is also due to the publishers, is in some sense killing the system, because if the review level falls below a given threshold, at some point there is no point in going through a standard review process, because there is no added values in going through that review. So you just produce your paper, you put it somewhere, and the people look at it if they want, and that's it. And if you are in the hype, you are in a, let's say, famous team, very visible and so on, people will have followers who will read your paper because it's you. So we are shifting from scientists to influencers. And that's a bit, scary for me.
Yeah. So how does this, translate, and what are you trying to achieve with your new position at Sorbonne, the AI Center? Could you maybe tell a little bit more about your place and kind of your vision to how to do, I guess, AI for science and AI for engineering, and maybe take some of those rigorous things that you've taken from the fluid mechanics world into this side? I love your shiny new office, so I wanted to hear more.
Yeah. Well, actually, in Sorbonne, we have this center, SCAI. Sorbonne, at the beginning, the name was Sorbonne Center for Artificial Intelligence, which was created 7 years ago, at the beginning of the AI hype, because we had strong teams in computer science and also in applied mathematics working on that. So basically, at the beginning, SCAI has been created by applied mathematicians and computer scientists, alongside with some people from humanities and from other sciences, for instance, computational biology, this kind of things. And it has helped a lot in making AI at Sorbonne visible. They have generated a lot of activities. At some point we have been labeled by the French government as cluster. So now the C in SCAI stands for cluster. And these clusters are sort of centers of excellence in France. There are 9 of them, which are supposed to foster research in AI, training and transfer to companies. And every cluster has its own specificities, but based on my own experience and based on the very large scientific community at Sorbonne, I said, well, right now everybody is looking at AI for science because science is actually going to be deeply modified. The way of doing science is going to be deeply modified by the introduction of these AI approaches, which is not the machine learning approaches for improving predictions or speeding up predictions, but also reasoning tools and models for automatizing labs, AI agents, and all that. And I said, well, the difficulty with that is that when you apply this to science, you have several problems. First of all, you are not dealing with random data. It's not images. It's not video. It's something which has a deep physical meaning, which is known only to experts from the discipline. So you can train a surrogate or whatever, or a foundation model using, chemistry data. But if you don't have a chemistry by you to explain if what's coming out of the model is, makes sense from a chemical point of view, or is just an hallucination, you don't know. So that's where it's extremely important to connect people from computer science and the disciplines, and also people from mathematics, because they can help with the mathematical foundations. What I dream of is the equivalence, the Lax equivalence theorem for machine learning. That would be the Graal, something that ensures that if you put more data in your model, at some point you are going to converge to something. But, that would be great. But so the idea would be to have all these people discussing together. And then I realized that some problems you can have in one discipline, for instance, in high energy physics, you have big data. These data are structured. They encode causalities, because the particle I'm capturing here at this moment comes from a jet which has originated there. And the particle have undergone some decay process and so on. And they call this actually jets of particles. And they say, this is the same you can have in a turbulent jet, because the jet is originating from, a slice or something, a slot. And then you have causalities of turbulent, of laminar structures, which eventually become turbulent, and then they are modified, they are transported. So we have the same problems, and we have to encode these causalities, because trying to learn all the physics, all the chemistry, all the biology from scratch using brute force training on data, it's not efficient, because we know the physics. If we know the physics, let's use it. But the problem is then, how do you really encode that physics? First of all, you need to know it. So it's not the computer science guy who is going to know which are the constraints, which are the most suitable for high energy jets, right? So we need the communities to work together. And also some problems which have been solved about causalities, in the energy physics community, can be useful for fluid mechanics and covers it. For instance, I have talked with people from plasma physics. So in some cases, they have Navier-Stokes plus the magnetic field. They have problems of closures, because they cannot resolve all the scales. They need to use constraint models, so they have closure problems. And maybe something of what we are doing with turbulence modeling can be reused in that field. I'm collaborating with volcanologists, because in volcanoes, you need to characterize the geology of magmas, and you cannot measure it. And you have simplified models, which are not accurate enough. So you can use the techniques we use for turbulence modeling to improve the rheology of magmas. So that's where it becomes exciting to share knowledge across the different scientific communities, instead of having every guy in its isolated department reinvent everything from scratch, because we are reinventing the wheel otherwise, And that's how we are trying to, I'm trying to animate this community, and we have a seminar now called AI for Science, and hopefully we are trying to apply to funding opportunities, even if they are not funding. Just the fact that we are around the table and we are thinking about what we could do together is already something which helps building the community. And then, people start to collaborate, and I think it's beneficial to everybody. That's my hope, at least.
No, it sounds fantastic, and I totally agree. There's lots of, I like the ideas of these multidisciplinary centers, particularly in the age of AI. I think it makes complete sense. And as you say as well, helping be a bridge to, I guess, industry and startups and things like that. That makes complete sense. I guess maybe as we come to the end, all of these new things, all of these topics that have come up since I guess you did your original studies, how does this affect the education system? What should young fluid mechanics researchers be picking today as their PhD topics or their undergraduate? What will prepare them for the next 10 to 20 years of the world we live in?
Yeah, I think we are in a very critical period for education because, well, you and me have been educated in a period without AI. So we have been taught how to solve problems without the help of AI, to how to interpret critically the results, and how to look for information, and how to check if what we are doing is good or not, and so on. The problem is that the new generation is AI native. So I was hearing because yesterday at the radio they were saying that many teenagers now who are going to vote for the first time are asking AIs what should they vote, because they trust AIs more than politicians or more than the classical media. Okay, and they are doing a little bit the same with the school teachers and with university professors who are not prepared to that, because the students are smarter than we are, and they know how to use AI to solve their fluid mechanics problems, to solve their thermodynamics problems. And you have still teachers who 6 months ago were not even imagining that the problem had been solved by an AI. So right now, many colleagues are scared about the fact that students are cheating with AI. But for me, the problem is not only cheating. The fact is that some students are basically, delegating the task of thinking to AIs. That's much more dangerous. So what I think is that we have to rethink the whole system, and many tasks which were, I teach you how to solve second order linear ordinary differential equations, and you just have the technique to solve that. That's no longer useful, because, ChatGPT knows to do that very well. The problem is we should teach the students how to analyze the results and how to understand if the result is correct, if it's an hallucination, how to formulate the questions also. Because if you don't know how to ask AI correctly what to do, AI is going to do something you don't control. And if you are not cultivated enough to understand the answer, you are just going to accept whatever comes out without criticizing what's coming out. So I think that we have to move the shift. So instead of teaching techniques and or just notions, we should teach critical thinking, and that's harder because it implies a considerable modification of our teaching problems and the teaching approaches. It's not easy to do, especially in large universities as we have. We have courses with 500 students. It's not easy to have to change all the teaching procedure, but this is something we need to do, because without critical thinking, basically humans are going to lose competence, and in case AI is not working, what do we do? And I had a very nice metaphor from a person from the European Committee who said, well, when you are a pilot of an aircraft, you are 800 or 900% of the time, you are going to use the automatic pilot. But in case of accident, the pilot needs to know how to drive the plane down to safety, right? And that's exactly that. So we need to be critical because we don't know where the AI is going to hallucinate. Even we need to understand if, for instance, sometimes AI is able to bring us notions from other disciplines, which are not our discipline. But if we have methodology, we know how to analyze if what the LMM is saying is reasonable or not. We know how to verify facts and so on. And we have general culture and language capacity to understand. Then we can control and we can be enriched as professionals, as scientists, as humans, and whatever, instead of being just, replaced like in Matrix. That's my nightmare. Matrix. Humans are just there to be pumped energy.
Yeah, no, it does seem that it's not universally accepted how best to do this from an education point of view. I've heard some go the other way and be almost, well, for an undergraduate, we will do lots of in-person examinations and basically no homework anymore because there's just no way of knowing the homework. And as you say, there's the other side, which is maybe a little bit more, do a presentation to explain how you got there. I kind of lean a little bit more to the first one at the right stage of your career. I guess this is more like even a secondary school, let's say, before university. There's certain things where I just feel you have to know it because, as you say, what if there is a moment where you don't have access to the AI tools? I feel there's like a transition point when you can expect, like if you're doing a PhD or certainly a postdoc, I actually think AI is a fantastic help and will make you more productive, make you be able to do more things, help you achieve what you want to do faster and better, and ultimately get what would have taken you a month to write some coding, which wasn't your main task. It was just you had to do it to get there. AI will accelerate it. But if you're at the undergraduate level, or still at school or something, I feel that's probably where AI should only be used to help you learn something. But it shouldn't be used like a calculator almost, or you will just not understand the fundamental theory.
It can be used as a mate, because you can, tell the AI, ask me questions. And you give the answer, and then the AI can analyze.
Like a tutor.
And it makes, learning more interactive. In my research, sometimes I feel alone and I don't have a colleague to discuss about a point. So I take an AI and say, what do you think about this idea? And so we start a conversation, and that's useful. And the AI is bringing some ideas. So
or explaining new topic. I often do that when I'm trying to, and you can ask it. And the great thing I find is that it has these different levels where you could say, okay, sometimes I'll ask, like, can you show me that in a code? Like, how would you actually code this up? Which would be hard for a tutor to do instantly, like a person to be that flexible.
To move from reasoning to code and back and so on, because you are easily lost in, coding details and so on. That's actually great. But the problem is to explain to the young generations that that's the way probably to use the AI, more like a companion than like an entity that is going to do the work in my stead while I'm, I don't know, playing video games or something. That's not the point. And they need. So the problem is to explain them what are the risks and why they are missing something if they use AI only for that. So I can understand that sometimes you need to accelerate, you have to give a report or you are a little bit in a hurry. But if you do that systematically, then basically you are missing your education because it's not you who is going to be educated, but the AI.
And I think in some ways it'll end up creating a bit of a sort of two-tier system where in some ways people will become in some ways quite capable of doing some jobs where it requires them just to be, a functional user of these tools, but it will stop you from maybe being the inventor or the innovator. And there feels like to be fair, you could probably still do quite good at a job because these AI tools are so good. But I feel there must be some points where that lack of deep understanding will come and bite you. And so, it's the challenge.
True. Yeah. And also in very specialistic fields, so we are in very specialistic fields. So I don't think that the AI has been trained enough. So that's where, you bring the new ideas. Maybe the AI strengthens you, accelerates you with the coding, or allows you to make connections more quickly and so on. But it's still you who are bringing the ideas. And if you,
although that I do suspect will also be, succeeded by AI, because the AI scientist or the AI engineer, I have to say, I still suspect actually that it will be able to come up with as many ideas as we will be able to do. Maybe not the, Einstein new completely breakthrough thing, but it's certainly going to be an interesting test. Of, given that the whole, your center is a good example of it, I do get the sense that AI for science or AI for engineering is now becoming the frontier. It wasn't 5 years ago. It was sort of seen as a niche area. I get the sense now that the world of sort of physical AI and AI for engineering and AI for science is becoming a hot topic. And whenever it's a hot topic and there's lots of investment and money put into it,
there is some overselling. But yes, I guess that's the frontier. And I want to believe that, even if AIs are becoming more and more powerful and potentially they could even win a Nobel Prize at some point. If you think about AlphaFold, for instance, what's new is the fact that in a few years they could discover thousands and hundreds of thousands of proteins, which are much more than the 2,000 and something proteins they had discovered during the past 50 years. So every protein structure was a PhD thesis. And now you can generate plenty of them, just with this AI. So what was new was the fact of being able to accelerate so much, but still without the knowledge of the proteins from the past, it wouldn't have been possible to have that. And the same for climate. If now climate models are so good, that's because for tens of years, people have developed better and better climate model, the classical ones, and they have done data simulation, and then they have done all the reanalysis from the beginning, and with that they have generated the huge databases which can be used by the models. And also, everything is like that. That's because we have huge amounts of human knowledge accumulated over years, which can be injected in these models. But once all the knowledge will be generated by these things, probably, I don't know, maybe at some point they will become so intelligent. We have these emergent phenomena. They will be able to create something new that happens in very complex systems. But I hope humans have still a role to play.
Oh, yes.
And that, and that instead of being replaced by these AIs, one of the person who participates, so Jesse Taylor, he's a physicist from MIT, and he participated to our AI for Science launch day. And he came out with this metaphor of the centaur scientist. And I found that as a beautiful metaphor, because, if you are 2 men and not enough oars, you are too slow. If you are two horse and not enough man, you cannot reason. But if you have half man, half horse, you can go as fast as a horse while having all, the creativity and wits of a human. And so, well, I adopted this idea and say that, well, our role would be to train the next generation of centaur scientists and centaurs professionals, and not just horse. Which would be...
I like that. And that's probably a great way to end this in the sense of, I agree with you that it's about the coupling of human and AI. It's about being progressive and optimistic about AI, but not forgetting the sort of human role in it. And I would argue that today the human specialist is needed even more, because to help develop these AI models and make them accurate and point them in the right direction. But maybe we need to talk again in 2 years' time and see where things have gone. It'd be interesting just to listen back and see, as it shot off like this, is it the same? Is it less? That will be an interesting. But I really enjoyed this discussion with you, and I personally always love working with you on various committees and things. And been a pleasure to spend this time with you.
Okay, thank you for the interview. It was very nice to discuss about all this.
Great, thank you.